We had the idea to invite Father Corboli to give this presentation and some page on Astronomer filter, because when we read a speech that the Pope was planning to do at the University of Rome, of La Sapienza in Rome, we were struck by a sentence in particular. I quote: "The danger of the Western world, to speak only of this, is that today, precisely because of the greatness of its knowledge and power, man will fail to face up to the question of the truth with the capital T." And so, if thinking to my everyday experience of grad student in physics, I realize the importance of this sentence, and I see that most of the time we limit the scope of our reason to what is merely measurable. So Father Giussani used to define reason as an openness to reality, a capacity to size and affirm reality along its vectors. So reason is the capacity to grasp reality in all its aspects, not just the measurable ones. But sometimes for the work that we do, we limit ourselves to that, to the measure, and what we can measure, what we can deduce just using our logic. And so sometimes I see in my daily life, I set aside the deeper question that the wonder and know that comes when one looks at the reality we have around. So a sense of the question that comes when we look at the beauty of the world, something probably will show us. This deep question about what's the meaning of all. Also pose question for our reason to study. And so the consequence is also that our faith is not completely reasonable, because we don't engage our reason in our faith. We think faith is something, reason is something else. So I will believe with my faith, and I will measure, understand with my reason. So we ask Father Corboli, that is a great scientist and also a great to help us in putting the things together.
I wonder if we could have the lights out at the back. I think there'll be enough light coming through next week. Good. And it's great to be with you. Thank you for inviting me. We're going to have a certain amount of physics in this. Don't worry if you want to ask a question, I don't understand it, or enjoy the pictures and enjoy the general flow of things. Okay, so you're welcome to. If you don't understand or something right on your mind, do ask. It's almost a discussion. So, passing faith through an astronomer's footer. I was pointing out, this is the logo of the Vatican Observatory. And what you'll see here is the sphere of St. Peter's, and of course, an observatory dome underneath. So, what's the observatory all about? It's, that's quite a strange distortion. Let's leave it like that. This is the whole sky view from Mount Graham. Now, somebody's asking about the observatories here. Basically, the observatories in all directions from Tucson. So to the north of the Catalinas, to the south on the Santa Ritas, you may well know to the west, Kitt Peak, and to the east is the most recent one, observatories on Mount Graham. And it's on there that we have our Vatican telescope in this part, dedicated about 15 years ago. And so this is the sky that you can see from Mount Graham. And what you see, the Milky Way, this is basically our galaxy. And if you can imagine this arm stretching down the other side, that'll complete our galaxy. And what you also see is another galaxy here, our nearest big galaxy that we can see. It's the Andromeda galaxy, so this is big in the summertime. And this, where Jupiter was when the picture was taken, so that's that splotch. Otherwise, lots of white stars. That's Tucson, if you're wondering, and Davis Mont. And that's Phoenix, so a lot of light from Phoenix. And down at the bottom, we're looking to the south, will be Wilcox. Okay, so it gives you an idea of orientation. And this is just near Safford. Anyone been to Safford? Yay! It's really quite remote. So, but the question is, how do we learn about these things, these stars and everything there? And what I'm suggesting is, a way we do it is through optical filtering, not chemical filtering. You do chemical filtering when you're making coffee in the morning. Okay, so that's it. This is optical filtering, and just what happens with that? Well, light with all its colors on a black surface gets absorbed. Light with all its colors on a reflecting surface, everything gets bounced off. Light with all its colors, if that surface is yellow, absorbs all the colors except for yellow, which happily bounces off. As a way, yellow is extracted, yellow is emphasized, we get yellow. Well, haven't we lost all the other colors? How about all these? Is that a shame? Well, no, not really. And just remember the way that something like television or your cameras work. This camera we have at the back here, how that works. What it needs is to make the color, it needs 3 pixels or photodiodes, they're called here. 3 light-sensitive diodes. And then these colors, colored filters, blue, green, and red. And so just the blue light goes to the left-hand one, just the green goes through the middle, and just the red through the right-hand one. But if you combine them all together again, you get your original color. So yes, you've extracted color, you've filtered, as it were, thrown away the other colors, except for blue here. But by then combining them all together, you're getting something enhanced, you're getting the original colors back. So that's the idea of a filter enhancing things. And we can see that in practice in astronomy in this way. This is a picture of a galaxy taken with our Vatican Advanced Technology Telescope up on Mount Graham by Father Jose Funes, who's now our director from Argentina. And Jose and colleagues took this picture. It's really, without a filter, it's got all the colors in though. Here it's looking sort of whitish and yellowish, but it's got all the colors there. And then he used a filter for just a tiny part of the red. And this is a picture of that same galaxy. Can you sort of match up bits on the right and the left and convince yourself it's the same? Yep. I'm not trying to pull the wall over. Okay. So, what we are seeing there with this hydrogen alpha filter, it's called, that just lets through a little bit in the red. What that emphasizes is the blobs are where there is intense formation of stars. So starbirth activity in the star alarms, not in the middle. Very bright in the middle when we look at it in all the colors, but through a filter, okay, we've thrown away lots of the colors, but we've gained enormously in information. It's told us about where the stars are being formed. So, okay, that's the idea of filters. And, okay, so we're going to discover using filters, so looking through in various aspects of the heavens, and kind of what does it tell us in the little reflection. Who among you, don't worry if you've not, has not heard of the Doppler effect? Or you've heard and you're not quite sure what it is? Okay, good. So, the Doppler effect is something to do with the way that waves work, propagate. When they propagate from something stationary on the top here, so this is this train on the top, and it blows its whistle. When they propagate out from that, you hear the same pitch, whether you're standing in front or behind or on either side. It's the same pitch. Okay. But if that train is moving in this forward direction here, and it emits a sound, then the waves of sound get crunched up to someone standing in front. They presumably wouldn't be standing in front for too long, but anyway. And the waves get spread out to somebody standing behind the train. So from the woo in front, if the train is moving, we hear woo, and behind we hear woo. So the pitch has gone up in front and lowered at the back. And the reason is because the waves are being crunched together. The waves of sound are being crunched together as the train is moving to the forward, and they're being spread out as you hear from behind the train. Okay? Got the idea? So by the crunching, or as it were, the pitch, you can tell not just that the train is moving towards you or away from you, but how fast it's doing so. Okay? Same thing we can do with light as well as with sound. And this is done, this graph there shows what is done for galaxies and finding, as it were, the pitch of the sound or the light that's coming from them. And what is being found is that, again, the lower the pitch, the faster the galaxy is moving away from us. So the way to think of it is these galaxies up here are low in pitch. It's really a light wave that comes to us, low in pitch, and these are high in pitch. And what there is a relationship between, and so the ones low in are really going much faster than these that are relatively higher. So what we find is that this on the bottom is apparent distance. The nearby galaxies are not moving away very rapidly. The furthest galaxies are moving away extremely rapidly. Okay? Near, fairly slow going away, further away, very fast. What that is due to is the original expansion of the expansion of the universe that comes from its beginning you've heard of the Big Bang, when everything was together in a singularity, exploded, and has been expanding out since. And the effect of that is that the further away we look, the faster the galaxies are going. Now, you'll see something. Yeah.
I had a philosophy class once, and we talked about that everything's moving away.
Yeah.
He also said that astronomers have noticed that things are slowing down. They're not moving as fast as they used to. Is that true?
Actually, what's happening is they're moving faster than we expect them to. The further away we look, the faster they seem to be going from what we expect, from a kind of a uniform expansion. So that's the kind of the current puzzle that people are thinking about. And you hear things like dark energy as something to explain. Is that the term?
Yeah, I just been trying to see if this argument is
Yeah. So it's right. The further away they're moving faster than we expect. At least back about a third of the age of the universe, things are going faster than we expect. And for the moment, let's take it as fairly linear. But that is a good point. There's the things that we are glossing over. Again, that are, as it were, filters, are ways of finding things out, are telling us about the universe. That there's some real strange things going on, and that's fascinating. The Hubble Space Telescope some years ago, it's 10 years ago, maybe more, just after Christmas, stared at the same spot in the sky again and again and more, orbit after orbit as it went round the Earth. And what it was doing is trying to go fainter and fainter and fainter. Okay? And as a result of that, this movie was made. So,
We're simply handing across the Hubble field, and every single thing that you see is a galaxy. Many of these are giant galaxies like the Milky Way, big spiral galaxies that contain 100 billion stars or so. This picture was taken by Hubble Space Telescope, looking out of the disk of the Milky Way, so there are very few stars in the way. But there's a star, the white cross, near the yellow spiral galaxy. There are lots of other kinds of galaxies in this picture. Something you have to appreciate if you look at an image like this is that you're seeing galaxies superimposed in front of other galaxies. We can see all the galaxies that are reasonably bright all the way out to the edge of the visible universe. It would be wonderful to be able to see these galaxies not stacked on top of each other, but spread out in space and time. And that's what this video is about to show you. It's impossible to measure the redshifts of about 500 of these galaxies. And based on these measurements, we can estimate the redshifts for all the rest, and thereby their distance. That's what people who made this video did. Professor Kenneth Lanzetta and his colleagues at State University of New York and Stony Brook. Soon, we're going to zoom into the picture using this information. We'll first see the nearby galaxies go sliding away toward the edge of the picture. Then, we go farther and farther in. Only the galaxies that are very far from us will still be visible. Now, turn the zoom in. We're already about 1 billion light years away. That is, ones that were just disappearing from that far away. The colors that recently entered, the back of the galaxies look somewhat yellow, reflecting the redshift fact that the light has been shifted toward the red end of the spectrum by the expansion of the universe. There's still plenty of big galaxies. We're now looking about 5 billion years back. Now, at about 7 billion years back, halfway back to the Big Bang, there are no more big galaxies in this picture. Perhaps they have been time to form yet. Now we're back for the first 4 billion years. Now the first 2 billion. If there were galaxies there, the whole Space Telescope would have seen them.
there were galaxies there, the Hubble Space Telescope would have seen them. That's back at 2 billion years from the beginning, some 12 billion years back in time. It's sort of difficult to grasp that kind of time, isn't it?
So is it reasonable to think that there's galaxies beyond where the light reaches us right now?
The suggestion there was that no, that you don't see galaxies beyond, 2 billion years from the beginning of the, from the Big Bang. Exactly.
But why?
Because it took a while for them to form, for things to clump together. Perhaps what formed first were massive stars, and then later galaxies formed from material spewed out from those stars, or even pushed together somewhat by those stars.
Like, are there things out there that we could never see in our lifetime because the light hasn't reached us yet?
There certainly are, yes. There's a part of the universe that's simply beyond 14 billion light years away, 13.7 if that's the thing. Or certainly if the galaxies were being formed 12 billion years ago, then beyond 12 billion light years away. There's still galaxy, or universe, let's say, there's still universe beyond that, but the light won't have had time to have reached us.
What about, sorry.
This definitely is a philosopher here. But yeah.
Like from the center of things, so when we singular things, I don't really know, but like, I guess, is there like another order of where things can be? Like the speed of light?
Yeah, that's the limit. The speed of light is exactly our limit. So, go back to the time that the universe has been chugging along. And yeah, the speed of light limits how far we can penetrate into that. And say that, the max is certainly back to the time since the Big Bang, so 13.7 billion years. And the suggestion here is that if stars were formed some 2 billion years after that, then that's a limit of how far we can be able to see. Okay, now tell me what's beyond that. And still, yes.
How do they know what they're seeing beyond where they say the galaxies end? How do they know that those stars aren't really galaxies, they're just so small it appears to be a star or something?
And it could, what there may well be are the very first generation of stars, but they are so faint compared with the galaxy that we don't see them. So I think we can say there's nothing beyond what is suggesting there aren't any galaxies, or certainly not any moderate-sized galaxies beyond that.
What I'm saying is, could it be there? We just don't have the ability to see that part clearly enough?
This was suggesting not, but let's see, and that's why we're building bigger telescopes.
Yeah.
Bigger mousetrap, see if we can get more mice, more galaxies. Yeah, that's always good. So it's proclaiming the glory of God. It is an amazing universe. That's really the point of this. And I see the heavens, the moon, and the stars. What are we that you should keep us in mind? Yet you have made us little less than the God and the glory and honor you crowned us. And we have strangely an ability to at least come to some understanding of this and to try and build better instruments to get even more understanding. It's our nature and maybe reflecting something of God and what God is doing. A pretty picture, basically, within our own galaxy, in the regions where there are new stars, and it's the new stars that are igniting within these clouds. It's actually that blueness is dust that's scattering the light of the new stars, and the pinkness is the gas. It's also associated with new stars being made. The gas shining or being excited by the intense light of these stars within these cocoons surrounding all this material. And there's that nice little pink glow. And so when you look at it a bit more, the pinkness, you'll see also, somebody sort of put that black brush there. Yeah, it sort of is a black brush dust particles. So there's nothing there. There's something, there's lots of dust, and the dust is preventing any stars behind coming to us and seeing that. So fascinating things there. God, beauty's self and beauty's giver, which is one of the poems of the Jesuit Gerald Manley Hopkins. And that gives us a sense. Again, one of the tools then for finding out about things is just light and taking pictures. What I'm very much involved in is spectroscopy, or the rainbows of stars and nebulae. And okay, Newton split up with the aid of a prism the light from the sun and saw that it was all split into its components there, and then actually put another prism here and combined another prism, imagine here, and then combined the light back together and got white light out of the other end. So this is the nature of light. Okay, on the top we do see a rainbow there going from the red down to the blue, but then there are places where the light is missing, and this intensity tracing with these teeth coming down shows you that light is missing in those spots. Why is it missing? Well, we have to get acquainted with our friend hydrogen, the most primitive atom, okay? Because it's got a nucleus in the middle, a proton in the middle, okay, positive charge, and an electron that can be said to be going around it, though that's just a model of what happens. The electron is a wave as well as a particle. And it's as a wave, you can imagine that it has to join up with itself. The wave has a certain wavelength, okay, between the top and the bottom of the peaks and dips as the wave goes. And the wave, as it goes round here, has to be an exactly integral number of ups and downs. So as it were, its mouth joins its tail exactly, despite the fact you've got a wave. And that's why you can only get the electron going around these various orbits of the number 1, 2, 3, 4, 5, 6, up to 7. So the electron can't go around the nucleus any way it likes. It has to stick within what we call discrete energy levels, or those circles. So the electrons sorted into levels according to energy. You can see what that means a bit in practice. Let's zap a photon of energy into this hydrogen atom, hitting an electron and getting absorbed there. It's just got exactly the right amount of energy to kick that electron up into this orbit, which again has got a nice integral number of wavelengths all the way around it. And so we've got a nice, happily excited electron there. Can you imagine? Just like a 2-year-old or a 4-year-old, or okay, happily excited. And then what happens? It sort of flops and sort of rests, and kind of the energy goes out. So the energy going out there, and the electron then transitions back down, let's say, to its former level, or in fact to any of these other levels. So that's when it goes rest and drops down, and you get some peace. So that's what's happening. And so there's a very discrete amount of energy, the exact amount of energy, that either kicks the electron up, or the electron releases as it jumps down a level. And that's what's happening, and shows us these gaps in the light, in our spectrum, in our rainbow. That's why we've got dips. What's happening, again, just look at it, we have what's called an electron in a ground state, so nearest to its proton, gets some energy, thanks to a photon, jumps up one energy level, and then perhaps anything might get some more and jump up another, or release that energy and comes back to its initial spot. So that's transitions between the first energy level and the second. If we get, and that's the one along here, if we get instead transitions, enough energy to kick that electron up into its second excited state, second level, and then it drops back into, from the second to the first, the energy that comes out is in the red region of our spectrum. So we get, as it were, a red flash from that electron dropping back from the second energy level to the first. And that's the pinkness, redness that we saw in that nebula. So that's where that comes from. Ah, okay, we've got lots of physics in there. All that redness you see, it's something like Eta Carina, you know, that pinkness again we saw in that nebula, that's where that comes from. It comes from electrons playing around, hydrogen electrons playing around in the hydrogen atom. That's what's happening. It's right at the very tiny level that we're getting that beauty and that deepness, that beauty that the top is talking about.
So the reason why it's getting on the second is the heat, or I mean, what's making the difference?
Yeah, what's making the hydrogen gas excited? Yes, it's the radiation coming from the very bright star that's nearby. And here we have maybe one, maybe two very bright stars, some 15 times as massive as our own sun. And I think in the middle of the 18th century, it suddenly brightened up and became the second brightest star in the sky. So things are happening there. It's called a luminous blue variable. And this star might well explode sometime soon. So duck if it does. And then we really will get some excitement. Okay. No, it's not so much heat as the radiation coming from gas. Yes, there's a sort of heat or excitement, there's energy exciting it and making the electrons jump up into a higher, more excited orbit. But and then they decay back down, and so you get that energy out just in the red, let's say, or just
So
the...
it doesn't have a different color. For example, it gets really excited. Does it go into a different color?
Yes, it can do. If it jumps down to a lower energy level, so say it jumps between energy level 3 and then back down to 2, sorry, back down to 1. Yeah, you're getting more energy than jumping from 3 to 2. Okay?
But it doesn't give off the same color?
It will give off a different color. More energy means a bluer color. Okay?
So, is that why the green filter shows where a star is being born?
Yes, because it shows you that the gas left over from the birth of stars, and the fact that there's something really powerful, a really powerful star there exciting them, and they tend to be the new ones that give off a lot of radiation. Okay? Yeah. At the top it says, it's sitting on my screen, sorry, it's chopped off. At the heart of matter. And we've been just talking about the heart of matter, how electrons play around with radiation. This is the heart of matter, the world heart. Okay. According to Pierre Teilhard de Chardin, the heart of God. So that's the point of trying to understand, how electrons play around. Because this is matter, interacting with radiation playing. And it's been said to play by God. When Eta Carina might well do this, go supernova. This is the supernova called the Crab Nebula. It's 1054. It was spotted by the Chinese as this new star, this guest star in the sky that you could even see in the daytime. It was so bright. So, wow. And that's what it looks like now through our Bat telescope. Okay? And all these tendrils are expanding out. And if we took another picture now, we could see that that's spread out just a tiny little bit. And right at the middle, powering it all, is a pulsar, it's called. the optical signal from which was first detected by astronomers here at Stewart Observatory. First found in the radio, but that it was, there was an optical corresponding to that was found by astronomers here. It flashes 30 times a second, so it's rather tough to find. Okay, we've got to bring it fast. Okay, all this material spreading out, well, let's gather it again together. Gather it together, it's got a little bit of rotation. Things accumulate, accrete on the outside, condense in the middle. And we have a star getting going, a star with its retinue of planets. And that's, as we discovered in the astronomy, perhaps the way that we get planets. Okay, very simplified of the picture. Is this sort of fiction? Well, the answer is no, because this again is a simulation of what Hubble telescope found in the Orion Nebula, which you see in the winter time, that indeed is full of these little globules. Just floating away in this region where stars are being formed. Let's look at this one a bit. There's obviously something happening. Lots of gas and stuff is going away. There seems to be, that's what's doing it inside. Eventually that actually pushes all that this cocoon away. And doesn't that begin to look rather like what we've been seeing there on the right-hand side, the way in which stars with their retinue of planets are formed. So all this matter that gets spewed out is something that, at least in the case of our own Earth, has produced life. So that's, again, an aspect of our universe, life produced. The father of spectral classification, Angelo Secchi, a Jesuit who lived in the mid-19th century, and it was he who observed over 4,000 stars, different stars. He had many more spectra, but and classified them. So the first person to sort stars out, finding that you could definitely sort them out in some kind of an order. He did his work from a rooftop in Rome, and the rooftop that they're pointing at, where his equipment was on, was the top of the, who knows which church? Okay, on top of the San Ignacio, the Ignatius Church in Rome. I didn't say Jesu, but that's the other major Jesuit church. On top of San Ignacio, when you walk inside the church of San Ignacio, St. Ignatius, it's a wonderful church and a glorious dome there you can see clearly. But then as you walk up, you begin to scratch your head a little bit about the dome. And then if you really look at it carefully and go from one side to another, you say, that's a painting. It's not a real curved dome. And so a Jesuit brother had used perspective to paint a dome, because while they had made all the pillars strong enough to take a dome, they never actually built it. So the top of that roof is flat and very strong, and it's just the perfect place to put an observatory. And so this is where Father Angelo Secchi had his telescope. And that's what it looks like today. The remains of that are his observatory on top of the San Ignacio. Wonderful, use what you can. You don't have a mountain, use a church with a nice, flat, strong roof. So, Father Angelo Secchi. And these were the spectra that he got. Now, no photography in his days, so these are drawn by eye, from what he observed with his eye. Okay? Fantastic. And what you can see from that is, yes, there are differences between the various spectra, the lights and the shades. What we're understanding is the shading part, is where light has been absorbed by the old electrons around that, that they're atoms. saying, lovely, I've got a nice bit of energy, I'm going to hang on to that. And actually it spews it off, but it spews it off in all directions, so your net result is to lose a bit in the direction that you're looking. So a little bit of energy missing at these bases. But that actually tells you, gives you signatures of the different types of stars. So here are the 4 major types of stars that Angelo Secchi found. Oh, the first thing is just to say, one of the lines comes from our dear Earth. It's nothing to do with the star at all. That A is actually oxygen in the Earth's atmosphere. But the other lines you can identify with various elements. There's our friend hydrogen alpha, our pink drop, making the pinknesses. Sodium, iron there. Hydrogen again, another of the transitions that absorbs energy. Hydrogen again, hydrogen alpha, hydrogen delta. Here we've got what's called the G band, which is a molecule of carbon and hydrogen. There's also some calcium next door, iron, magnesium. So all these elements that we have on Earth can be identified in the sun and in stars. And this type 1 with strong hydrogen lines, see them there, there's the hydrogen, strong hydrogen lines. Secchi called type 1, and that's like Sirius in the winter sky, the bright star in the winter sky. The top one is like our sun, yellow and sun metal lines as they're called. Metals are anything other than hydrogen and helium. We've got to keep things simple for astronomers. Everything else. And then the 2 at the bottom are type 3. I'm not actually showing here type 4. Which are like Betelgeuse, which is a bright star in the Orion, and Alpha Hercules is the one at the bottom. So that's a summer star. Okay. So, sorting them out, sorting the spectra out. This is a wonderful thing we have at the Vatican, except that it's now too much light gets into it out of Castel Gandolfo, so it's not efficient. But it has a prism on the top and a very wide field. The whole arrangement is like a very wide field camera. So it takes, when you put the prism on the top, spectra of a whole bunch of stars all together. And what do you do? Well, you sort them out according, in the way that Secchi showed. You classify them and sort them out, and you can do that. The modern way of sorting them out is with digital spectra, of course. So these wiggles are the digital spectra. So remember, this is something near to Sirius, this A0 star. These big teeth due to the absorption of hydrogen, and the little tooth there due to calcium getting absorbed. And then we can see other trace elements as things get cooler. This is, yes, a temperature sequence going from something like 15,000 degrees down to something like 5,000 degrees for the A5s. It's degrees Kelvin, so starting from absolute 0, but don't worry too much. It's kind of a degree Kelvin is like a degree centigrade. And certainly once you get up into the thousands, it's more or less. Okay. You can also tell the size of stars. These are all the A0 stars, remember, like Sirius. But actually Sirius is more like the one at the bottom. Notice how the hydrogen teeth get narrower and narrower as you go up. This star has a radius of about the same size as our sun, maybe 2 or 3 times more. But the giants here, as they're called, the 3 types, have a radius of at least 100 times that of our sun, so that's where they're called giants. And you can imagine that the top lot are called supergiants, and they've got radii of about 1,000 times that of the sun. So you can sort things out. By the aid of spectra, you can get to know stars. So if you have a whole bunch of stars like here in M103, you can get to know their personalities and what they're like. These were born at the same time, but as you can see, they differ from each other. There's a yellow star here, that's gone giant. It's gone through its main sequence burning phase. We'll talk about that a little There are the yellow ones at the back, and the faint ones, and the bright ones, and a lot is to do with what mass they were born with, what they've reached to. But with the aid of the spectra, you can sort them out. All kinds of different things. God produced many and diverse creatures, so that what was wanting to one in representation of the divine goodness might be supplied by another. Okay? Hence, the whole universe together participates in the divine goodness more perfectly and represents it better than any single creature, whatever. Diversity is good. So says St. Thomas Aquinas, Dominican. So he knew a thing or two about nature. Let's run through the life story of the sun. So 10 billion years, and we're going to run through it in a moment. Okay, ready? Remember, it starts as a great cloud of gas and dust in one of these lovely nebulae, and then decides to kind of clump together. And right in the middle, you know, the sun forms, and then its retinue of planets. Okay, it burns very steadily for a lot of years. Our sun is about halfway through that steady burning stage where it's fusing hydrogen in its center into helium. That goes on for a long time until the hydrogen is exhausted, and then the burning, as it were, the fusing starts to happen further out. The hydrogen gets fused further out towards the atmosphere of the star, and it's then that it becomes a giant. And our sun's going to become a giant very soon. Another 5 billion years. Okay. And then you'll see what happens at the end. So let's run.
Stars like the sun originate in interstellar clouds, parts of which contract under their own weight. Once formed, the star remains quiescently fused for 10 billion years, until just before it runs out of hydrogen gas at its core, thus becoming a red giant and expelling its outer envelope to reveal a white dwarf at the center.
Okay, that was quite a quick 10 billion years. We've never got the a fascinating story. I'm not trying to teach you astronomy in its details, but just say a fascinating story. And obviously, in our case, one that produces and sustains life. So if all goes well and we look after our Earth, we've got another 5 billion years before it goes into the red giant phase. Okay? We've got a lot of looking after to do. Okay. And so for the sun, just puffs off its outer atmosphere, and it has a peaceful death. And look what results. Or this. And the central white star is indeed the star that puffed off this cloud at the end of its life. These are pictures taken with the vacuum as showing it up on that ground.
This is theoretically after the accretion of solar planets in the solar system?
Oh yeah, this is the end of a star like the sun's life. Yeah, it goes into this what are called planetary nebula. And there's a white dwarf in the center there, which gradually cools down because there's no nuclear burning to power it at that stage. Okay. So that's a peaceful death. But if a star is something like 10 times as massive as our own sun, it's going to have this kind of a death. And you can see this is the star in question there. Okay. That's what happens to it. It goes supernova. And then really spews things out.
When would that happen?
What?
When would that occur?
Right, again, right at the end of its lifetime. But being a very massive star, it actually goes through its lifetime much quicker than our own sun. So,
But I mean, what type would do that? You said.
what type? Really, the stars that we weren't, kind of, we haven't been looking at hot enough stars as yet. The spectrum we saw aren't big enough and massive enough and hot. They're rather few, perhaps just as well, but they're also very, very important because all this material coming out from them is the material that is heavier than than iron. Okay? That material, all those elements all get synthesized in the very last moment of the star as it collapses on itself, gets to an incredible heat, explodes, and everything expands out as you saw there.
Is this similar to what causes that one that was, I think it was called Regina something? It was a very big explosion with a lot of red ink around it.
It could be, yes.
Yeah. Is that similar to what causes that? Because that looked very intergalactic with a lot of.
Well, maybe there's such energy in these that they appear as bright as the host galaxy. Just for a few weeks, a short while, they are really, really bright, and then obviously they decline with the brightness. So is that the sort of thing?
Yeah, there was one image that we showed. It was a very large explosion.
Oh, one of the images here.
Yeah.
Oh, yeah, the crab. Yeah, this is that's after a supernova explosion, yes.
Okay.
Yeah, so, and that's why the star was so bright that the Chinese could see it in the daytime.
Oh. No, actually the one before that. The one just before that.
Oh, Eta Carina.
Eta Carina, yeah.
What it seemed to have had is had an attempt but didn't make it. Or there's some activity going on with its surrounding. But if it is indeed 15 times as massive as the Sun, it is going to do this.
Okay.
Yeah. And this is the picture after, explosion of this. And this was discovered, at least the first discovery pictures were taken by a friend of mine that I know down in Chile. And, 1987, he was actually a student at that time, and just happened to take the discovery pictures of this. So sometimes it's called supernova Sheldon, but the technical name is 1987. Anyway, they made this something, got it easily into grad school. So. Nice result, supernova. And then, when everything dissipates, this is actually the remnant of a supernova. It's called the veil nebulae, naturally, but it's the remnants of a supernova. So again, and there's a little reflection here from the big A person who looks at the table and can see the universe is a person who can see the way. You can see that your own life and the life of the universe are one.
That's really good.
And knowing that, okay, in the Big Bang, we got hydrogen and helium, maybe a little trace of lithium and other very light elements, but that's it. All the other elements we've got have come through the generation within stars, and either the peaceful death has pushed the elements out, like carbon and nitrogen and oxygen out, or the real explosive events have pushed out things like gold and platinum and lead and other important things, potassium, yes, other important things to life that have been pushed out. So a person looks at the table and can see the universe. Everything we have there has come from stars in this way. In a way, it's come from the universe. Yeah.
So in perspective, the nebula is in front of those billions of stars? Like closer?
Most probably, yes.
Okay.
Maybe some brighter.
Because it wouldn't spread out that far, all those billions of galaxies, or all those billions of stars.
Yes, so this is, this nebula, you see the pinkness and the blueness. So again, we know the pinkness is from the hydrogen, exciting hydrogen. The blueness is from dust. So, that's what we're looking at, gas and dust that have been blown out from a supernova. But it's rich, mine that dust and you've got gold and silver. Yeah. Okay, get going. But that's what it is, yes.
I mean, like how big is that nebula compared to how close stars are to one another?
Well, again, yes, there are certainly these brighter stars, are kind of showing the spacing of stars one to another. So it's gigantic. The nebula now, yes, gigantic. But with a little stone of guarantee and maybe a little pushing from another supernova, you can clump all that material together enough to make it swirl together and become new stars. So it needs a little push to become new stars. But that can happen, through either the kind of waves that the galaxy itself produces in gravity, the kind of dense and less dense parts of our galaxy, or through a pushing from the explosion of a supernova. That really seems to be quite a mechanism.
So,
Yeah.
what exactly is a nebula?
A nebula is gas and dust. That's probably the best way to think of it. Yeah. Used to be called nebula, used to be called galaxies. They called everything that was kind of larger than the star, a nebula, because they didn't know. But now nebula is confined to gas and dust, and then galaxies we know what they are. But a galaxy obviously will contain within it lots of gas and dust generally. Okay. Okay, mindfulness. I don't know whether any of you have read mindfulness. The Miracle of Mindfulness. Mindfulness is keeping one's consciousness alive to the present reality. And so what, we've been out in space, but it's actually our present reality as well, I'm trying to say. Just like the reality of the table, the reality of ourselves. If we are really engaged in mindfulness while looking through a telescope or whatever we're doing, then we will consider the act of each look we take as an infinite wonder. A joy will open our hearts like a flower, enabling us to enter the world of reality. So, to be aware of the reality that's there, the stardust of which you are made. People have said nuclear waste, but I think stardust is much nicer. So let's be mindful of our place in the universe. This is our universe and we're here. That the very large is needed to fashion this world of ours. Remember the distances and the times. That a very long time, here we are, is needed for the emergence of life. How long since life emerged on our planet? So, what's your kind of ballpark? But that's a very primitive life, actually fairly soon after the Earth was formed. Maybe within 7 or 800 billion years. Just a tiny. So, human life? Rather less. Okay. Really little most. Okay. But the very small atomic processes underpin what we sense. You're sitting on atoms. Actually, you're sitting on basically emptiness, little protons and the electrons buzzing around. And it's not solid. Okay. And mindful. The diversity among stars and humans provides opportunities for fruitful relationships. So many things are different. That all life is interconnected. That the universe continues to evolve and we with it. Okay, continues. That one that surrounds us. Now, a little movie clip was taken of myself going to the telescope. That's the Vatican telescope up on Mount Graham. So driving along the road too. Okay. And yeah, this mindfulness, this presence in the universe, it's good to sort of reflect and stop what you're doing and say, oh, yeah, this is true. You know, it's almost the unseen, how we're underpinned by things, these physical things, where and how they come from, the age of, and that's where we are at the moment. Okay, it's sometimes easier for an astronomer, and sometimes not, because there's an awful business and a lot to do when you go to observe. So it's not easier, I think, for an astronomer to have this kind of mindfulness. It's something we can practice in whatever we're doing. Okay, just
Much of the work of the observatory occurs in the mountains of southern Arizona. Father Chris Corley is a Jesuit astronomer who conducts his research at the Vatican Advanced Technology Telescope.
This is Arizona.
It's the spectrum surrounding stars. A field pioneered by a 19th century Jesuit astronomer, Father Angelo Secchi. Chris explains his view of the relationship between science and faith.
You can then prove God through science. And that's what some people try to do, and that's never happened through all the centuries. But what it does, it reinforces one's faith. It gives it a context, a wonderful wide context.
The stars setting behind our telescope. Okay, photograph. So this is the camera left open for a couple of hours while the stars set. And now, of course, you know exactly what they are. What constellation are we looking at? Do you know? Straight up. Bright one on top, bright one underneath. Orion. Because this pinkness, that pinkness is actually not a star, that's the nebula. And we know we're looking at hydrogen. Okay, hydrogen would play there.
This nebula of the Pleiades?
There's nebulosity in the Pleiades, yes, there is.
But I thought it might have been the Pleiades because beneath Orion's belt, that was where Pleiades is.
It's not far away, you're absolutely right. It's not far. And this bright one here is Sirius. Remember Angelo Secchi's spectrum of Sirius? So, and okay, I've been explaining a bit about the astronomer's filter to you, the kind of tools that we use to understand the kind of universe that we're in and the kind of reflections that then it can give one, can give a person of faith, and how it can enhance one's faith. As I say, you can't prove God's existence in this way, but you can certainly say more about God through one's understanding of how things work and through one's science and through one's particular branch of knowledge. And so you're not all, some of you are scientists, and that's wonderful. You're not all at all. But you've all got some way and expertise, a way of being in this world. And I'd simply invite you to, as you were, use that to enhance your understanding of God, what God's like. Okay? So find your filters, the filter of your expertise, a filter. Okay, it's not all the expertise in the world, and that's why I say a filter, lets through only some of the color. It lets through, say, the yellow color, but not the red and blue. But in letting it through, it actually enhances our understanding, and that's what I'm inviting you to do in your own expertise. The motto that Pius XI gave us when he moved the Vatican Observatory out from the Vatican City out to Castel Gandolfo in order to get away from the lights of Rome.
God's created would you go to the door?
No, come and praise them.
God the creator is the
come and pray.
Yeah.
Come and
Praise
praise the creation
God.
of
Yeah.
God.
No, God the Creator.
Oh, God.
Yay! You got it, lovely. Okay, you know. Yeah, you got it. That's good. Good, well, and, you know, if you want, VaticanObservatory.org if you want to find out more about this. Well, I've got some new leaflets here. I suddenly realized that I had some. These are almost out of print. I'm going to sort of take some.
If I still hadn't chose my major, I might actually think about astronomy. Taking astronomy semester. It's pretty cool, actually. Do you need to be very advanced in mathematics eventually to do a lot?
It's probably helpful.
It's helpful. I think math is, I used to think I'm horrible at math, but I think it's something I can do with practice.
It's just
If you know the formula, if you know the formula and you have everything, you do the formula, then.
And so, you know, one of his examples is, you know, you're driving and you're stopped by a red light. And instead of cursing the red light, just, you know, just experience it. You know, that experience. Realize what is happening. Maybe you think of the photons that are coming through the color, you know, like the red. Okay, just experience it. Go beyond the effect and the annoyance it has on you, and just be present to where you are and what's happening. That's the suggestion. Instead of bolting your drink or food, savor it. You're eating an orange, you know, or
I have a question.
yeah.
You were talking, oh, sorry.
Save the salt. I think it was salsa then. So you,
Oh,
and
I was
wonderful,
like,
that wonderful burning sensation.
I'll be quick. When you had described that your knowledge of these things enhances your understanding of God, and my question to you is that there's a lot of people who might actually see the opposite and see that all these things about the earth and using science explains why these things happen, and they'll say, well, through all that research, how would you still say that God exists when you can actually see why all these things exist? It's through the stars and it's through, you know, gases and dust and all, you know, there's explanation. So how can you just go deeper into what you meant by saying that your understanding of these things enhances your understanding of God?
Yeah, and it's partly the saying that God is not physical. Okay. So in that sense, God is not, you know, of the material of the world, of the earth, of the stars, of the universe. So you can't prove, as I say, you can't prove God's existence through the material things because God is not material. So that's one thing. If you come up against something like that, you can't prove to them that God exists. What you'd have to say is that it's reasonable that God exists. That, you know,
Well, okay, then I'm going to challenge you because I think that when I explain or I say something to that effect, they'll say that there isn't really any reason or logic involved in God if you can't explain something. There is no reason involved in that if you can't explain it.
well,
So,
one would love then that person to explain why they exist rather than don't. Why everything exists rather than doesn't. What's the... Is it in themselves? They have their own reason for existence. And if they don't, then it has to come from somewhere. Oh, well, it comes from, you know, all the material thing from my mum and dad. You know, I mean, where did your mum and dad come? You know, and you go, and in the end, you know, existence is a mystery. And either you say it just exists, or you say it has to exist for a reason, and that reason is outside of it. And that outside of that reason is what we call it. Is that,
Yeah.
Yeah, the question.
yeah,
Yeah, I was gonna ask you, okay, you hear a debate over two terms that I find are not necessarily mutually exclusive. And people get an argument over evolution versus creation, which I never saw that causes a conflict between the two. Can you comment on those two things in terms of, do you see a problem, do you see that there's faith versus evolution, or do you think they coexist, and that one is an expression of the other?
What I see through all this, the development of things, I've been feeding principally the physical universe, that you might not call, we do use stellar evolution, but we might better say stellar development or something. But it's not actually bad to use evolution, because there is very much a parallel with biological evolution as well. I think it is how the smaller things come together to make something more complex, and that you see in the universe, and you see enormous variety. That no two nebula are the same; they each have their own special beauty. So enormous variety there as well. So yeah, what I'm saying is that the universe is showing that the way God has chosen to create is through development and evolution.
That's exactly what I was saying.
So there is a conflict between creation and evolution. Well, yeah.
What does Benedict and the Pope say about that?
He acknowledges that, yes. That God's way of creation is evolution. And certainly that's very well accepted by John Paul II in that document that he has on evolution.
Fides et ratio. Fides et ratio. Faith and
ratio. No, those sections addressed to the Pontifical Academy of Sciences on evolution and the fact that it was, one of the quotes is no longer a hypothesis, that it was an established scientific theory, which doesn't mean to say, it's all true. The nature of science is that it's going to develop, and get change in our understanding, but, it's something more than just a crazy idea. There's a weight of scientific evidence that it's a harmless, reasonable picture of how things come to the present. So that's essentially that statement. While also saying, and there is still a darn great mystery about the making or creation of humans, and each individual human, and that individual human's relationship with God. There is a mystery there which we don't yet understand.
The thing that I think people can never account for is the jump from molecules to living molecules, and then the jump from animal life to human life. There's two bridges that have to happen at a stroke. And
Any good guesses? So.
Well, I mean, I believe it was God, obviously, but other people aren't usually able to account for it. Like, why do these molecules that are made up in this organization, why am I able to move and think and grow and love?
Now, the thinking and whatever and loving is, that's something else, but the movement and why like that, then this is an evolutionary tree that you can go back and see how you've evolved
But
through the various
jump
ancestors.
from non-living molecules to something that lives and replicates and moves, whatever, like that's, why did molecules just start doing that?
I suppose a very simple answer would be because molecules had it in them to be able to do it. And given the right conditions, then yes, they would do it. Because, in some ways, yes, you're, it's the idea of, and yet also behind, yes, we're made of molecules, and yet not just molecules. It's you can reduce everything down to the molecules, but you haven't described, the biological, wonder that is any animal. So there's something more, a lot more than merely the description in terms of molecules. And so it's that is something that's called, people give the name to emergence. A simple thing is to say there's something more from nothing but. And it's something more to try and explain that. And what you can say is that, matter and chemical molecules have it in them to emerge. And this is their nature. Now, again, back to the question, where did this come from? And I think it's quite legitimate and rational to say this is a God-given property of molecules to be able to emerge.
All this, I'm sorry, go ahead.
Such as we finished the talk while eating.
Oh yeah,
Yeah.
yeah.
So let me give some announcement and then we will eat and we can keep discussing. So I want to thank Father Corbett for the wonderful talk. And so our next meeting of the Club Logos will be next Saturday at 5:30 p.m. So we have regular meetings every week in which we...
Jesuit priest who loves astronomy, how do you look back on things like the Inquisition and Giordano Bruno and Galileo?
Oh, well, I think it was political, right?
Bruno was clearly not Jesuit, So that wasn't done by the Jesuits.
I think with Galileo, he wasn't the first person that discovered that the world wasn't flat.
Well,
It wasn't.
no, it was he discovered Helios, and he wrote about heliocentricity as opposed to geocentricity.
Oh.
Yeah, that was a different one. Yeah.
I think with Galileo, what I've recently done is that the church was going to come back and say, yes, this is valid, but then he announced it earlier or something, so basically like a political move kind of thing.
Try to keep it a secret.
Well, basically the church was going to come through and do some documentation on it or whatever, and then he announced, let it